Yeah. So here we are actually OpenLane. So we will first git clone one of the repositories which I have custom made for this workshop. So in that Git repository, I have the .mac file for the inverter as well as the PMOS and NMOS Sky 130 spice models. So this is the Git repository. We will be sharing the links also. So this is also an introductory into how to clone something from a GitHub link. So as you can see, this was basically one of my internship works, wherein you make your custom inverter, you remove the definitions of the already present inverter, and then you use your custom inverter definitions, and you see if it works in the open environment. It was one interesting work. In this workshop, we will be doing something in the similar lines, but we will be creating a full new cell of ours, and then we will plug it into the OpenLane flow instead of removing the standard definition and editing it with your custom definition. So these are the files, these are the lists which we have. These are the timing lists. We will be getting into this shortly. But before that, our main interest is this. These libraries are the SkyWater spice model file for the NMOS and PMOS. So this is one of the basic tutorials on how to git clone something from GitHub. So if you click on this green code button, you will see this clone. So it's a URL. So you copy it and you go to your local system where was OpenLane, and you can close this one. So more tabs you have, more headache you have. So yeah, we'll clear. What all you have to do is just go git clone and paste it. So this will create a folder called VSD standard cell design in your OpenLane directory. It should take some time. This is copying all the libs as well as the Mac file. Yeah, we are done. Now, if you open up the do LSMan cell here OpenLane, you will see this VSD standard cell. And if you open a VSD standard cell, you will see the Mac file libs, what all we saw in the GitHub webpage. Okay, now our experiment will be focused on this section. So before we begin, we will first open up the Mac file and we will just see the different layers that is used in the building of an inverter. So since I told you don't have to build inverter from scratch, you already have it. So we will be doing a spice extraction as well as the post layout spice simulations. Okay, before we open the Mac file, we need to have the tech file, the magic tech file to open this. So we will do one thing. Anyways, we're working on this folder. We will copy the tech file to this location cell. That we will learn one command also. We will just a second. I'll do pwd. This is the location. I'll first go to the clear this also. Okay, let's open a new tab itself. The tech file for the magic is present inside the PDKs, Sky PDK, Sky 130. What's inside this? Yeah, it's inside the tech file, and it's inside magic. Yeah, if you do an LSMan cell here, and this is the tech file we're talking about. So we'll copy this. Make sure you do a copy, CP, and our location was this. Okay, so this is basically copying this Sky 138.tech file from this location, that is the libs.tech/magic, to the directory which we had just cloned right now. So that is done. Just verify if that's copied or not. Yes, it's here now. So you can basically type the entire absolute path, and then just like how we did for during the floor plan placement stage, where we want to see the layout, we do magic -t, we write the entire absolute location to the tech file, then we do left and then entire path. So this is a simpler. You copy it first. It's a one-time job. We'll just close this. Okay, we'll be working on this. Clear the screen. Do LSMan cell here. Okay. So this command we have used earlier when we were seeing the layout for the floor plan placement stage. You do magic -t for technology. Our technology file is what we copied right now. Since it is there in this folder itself, you don't have to give the entire absolute location. And then we need to the Mac file. This is the Mac file. That's it. This ampersand is used to free the next command prompt. If you don't use ampersand, this magic will keep the next prompt busy. So it won't free up the prompt. See, the background can see it has freed up the prompt. So this is my inverter. Just like layout, we'll first place our cursor somewhere else. We'll do an S. We'll do a V. It has been centralized. So these are the layers which you see are required for our inverter, for a basic CMOS inverter. So as you know, inverter is nothing but a PMOS, which is this, NMOS, the gates, the red line what you see is the polysilicon, and the source of the PMOS is connected to VDD, the source of the NMOS is connected to ground, the drain of the PMOS and NMOS are connected to the output, and both the inputs are connected to the and both the gate of both the transistors are connected to the input. So before we begin anything, let us just understand the layers. So on the right side, you see all the color palettes. These are basically the layers from which you can choose. So in SkyWater 130, the first layer is the local interconnect layer. That is short for local I. So if you see, this is the color. This is the local I. This is the first layer. Above that, it's metal 1. It's a purple, light purple color, metal 1. Metal 2 is a pinkish crossed. This is metal 2. You can, and then there is this envel. Envel is this, the solid slanting dashed lines. So let's, before we jump into any conclusion and say, like, assume that this is an inverter, let's say if our devices are present or not. So we know that when an N diffusion region, so this green is N diffusion. How do I say the green is N diffusion? We just go to the color palette, move your cursor over the color, and you can see on the top N diffusion. Just see on the right top corner N diffusion. And similarly, there's brown color, that is P diffusion. So we know that when an N diffusion, when a poly crosses an N diffusion, it's an NMOS. And similarly, when a poly crosses the P diffusion, it's a PMOS. It's well and good in theory. Let's see if it's true or not. So what I will do, I will just as we had selected the pins, if you remember during floor plan, we will move our mouse over this intersection area, like the area where the poly and the N diffusion is crossing. We will keep our cursor over there and we will press S. So S will select only that area. And then we will move to this TKCon window and we will do a what. So the what will tell is, what is basically telling us what is the highlighted portion. And what it says, you can see, it's an NMOS. So the definition holds true. That is, when the polysilicon crosses the N diffusion, it's an NMOS. That is correct. Similarly for PMOS, we move our mouse over here. Don't click on anything. Mouse over here and do an S. So again, we will do a what. That's a PMOS. So that's good. That is great. And so we know that the NMOS and PMOS, the gates are connected. That is good. Next, we will see whether the drain of the PMOS, the drain of the PMOS and the drain of the NMOS are connected. So in Magic, what you do, if you want to see if there are connections between two different parts of the circuit, all you have to do is press S 3 times. When you press once, it gets the place where your cursor is, that gets selected. When you press again twice, then the entire thing to which the highlighted area is connected to gets selected. So as you can see, the white is the output and it is now connected to both the drains of the PMOS as well as the drain of the NMOS. So that connectivity is fine. Now, according to CMOS definition, the drain, the source of the PMOS should be connected to the VDD, and source of the NMOS needs to be connected to the ground. So we'll check for PMOS first. We will do S, that selects that contact. So keeping your cursor over a particular object selects that object. So earlier we had kept our cursor over Y and we had pressed S. So that Y was basically a port. So when we press S again, the entire thing was selected. You can see the entire thing got selected. Similarly, we'll keep it over, this contact. The contact got selected. We'll press S again. The diffusion got selected, and this. So you can see this is the connectivity of the source of the PMOS to the VDD line. And similarly, when we go to the NMOS, we will do an S and S again. So you can see this entire thing is one connection. So how to build an inverter from scratch is all described in this. Git page, GitHub link. So this gives a basic idea about OpenLane, also what OpenLane is all about, what are the tools that is used in OpenLane for different functionalities. There is an introduction for something called LEF. LEF is basically library exchange format. So this figure is actually indication of what is the difference between a layout and a LEF. What we saw here is a layout, and this is basically how a LEF looks like. So LEF is basically, it will just have all the metal layers. It won't have all the information about the logic part. You can see in this figure there is no information about the logic part. So that is basically because you don't need for a PNR placement of any cell, any macro, you don't need information of the logic, because all you need to know is where are the PR boundaries. If I want to place a cell, I just need to know where are the pins of my cell and where is the PR boundary, where is the VDD line, where is the ground line. Only that information is needed to place a cell. So that is LEF, and LEF serves also the functionality of protecting the IP. So when you buy an IP from the vendor, so it is their product. They won't want their logic to be visible to the world. So they will, using LEF, they protect it. LEF is also in commercial tools. LEF is also called by the FrameView. And this is the introduction into how do you create a standard cell in Magic. So this is step-by-step creation. As you can see in this figure, that is just empty Magic window. And first you create a fixed B box with a 0, 0. The first 0 is the lower left. So if you see here, you can see some nomenclatures. Width and height is fine. the width and height of the box which you're creating. And LLX stands for lower left X value. That means if you can see my mouse, this is the lower left X value. LLY, similarly, lower left Y value. URX is upper right X value. URY is upper right Y value. So to define a rectangle, that is the only coordinate values you need to know, right? So yeah, this is the fixed B box value. We are creating a rectangle whose lower left corner and lower left corner is 0, 0. Upper right corner coordinate values are 138 and 272. So in microns, it is 1.38 and 2.72. So that is what it got created. When you do a property, this command, this is what gets created. So when you select on this box, just as I had told you before, right click, left click, and then when you type box, so that will give the dimensions of the box. You can see, you can try this. And following that, we build the CMOS step by step. So first we do, since I told you the first layer is the local eye, so we lay our ground and the VDD pins on local eye, and then since we will be taking connections on metal 1, so the standard cell rows are in metal 1, the power and the ground lines are in metal 1. I will show you where do we have the definition that why do we have to have the standard cell rows, sorry, power and ground in metal 1? Where do we have that definition? So this is and the dashed line, as I had told you before, that's the end. So you can see this is the end. This was the first thing we drew, the fixed B box. The purple thing you see hidden behind the dashed line is the metal 1. The bluish line, light blue line, is local eye. And there is one more layer, N substrate diff, that is actually behind this local eye. That is one of the design rules you need to fulfill if you want to have a contact. So now see, we just have made the layers. We have not made connectivity. So this square bluish checked contact is the contact between the local, the first layer, that is the local eye, local interconnect layer, and the metal 1. So that is the contact. That is called LICON. So we'll just go to the layout window and see where that contact is. So yeah, this was what I was talking about. LICON. LICON is the connectivity between the local eye layer and the metal 1. Before we make that contact, we have to make a contact between the, now for example, the PMOS. The PMOS is actually inside a well, the dash line inside the well. There needs to be a contact between the N well and the LICON. That is this. As you can see, that is more clear in the web page. You can see here this crossed line, that is the N substrate contact. That is the first contact. That is the contact between the N well and the local eye. So that first layer connectivity is done. And then you need to have contact between local eye and metal 1. So this is this checkered line, this checkered box is LICON. I have marked it here. Similarly, for NMOS, since NMOS there is no well, so it's direct P substrate. So you need to have first contact between the P substrate and the local eye layer. So that is this, you can see here. It's P substrate contact. And then you need to have a contact between the local eye layer and the metal 1. So that is this LICON, right? Hope that's clear. You just, it's logical, right? So for PMOS there is N well. Above that N well there is local eye layer. Above local eye there is metal 1. So to connect these layers, first you need to connect the N well and the local eye. For that you need N substrate contact. Yeah, N substrate contact. N substrate contact will ensure connectivity between N well and the local eye. Now you need to have a connectivity between local eye and metal 1. For that, LICON is used. Similarly for the N side, for the ground rays. So now that you have fixed your ground and the power and the ground rays, all you need to worry about is the logic. So you need to follow the DRC. So Magic is one of the interactive DRC tools. As in when you have a DRC, it will show up in the DRC. Right now the DRC is 0. So for example, I remove this layer. Okay, this is fine. This won't cause any problem. I will do one thing. I'll just try to remove this. Right, as you can see, the DRC has changed from 0 to 7, and this dashed line, this dotted line, white dotted line is the error. To know the error, you go to this DRC tab, and then you click DRC, find next error, and the tool will zoom into where the error is. And if you want to know what actually is the error, once the tool highlights this error, it will be written in the TKCon window. So these are the errors. These are the DRCs which you're seeing. This constraint, the physical DRC, is what getting violated. So this is important from the manufacturability point of view, because if the DRCs are violated, it cannot be manufactured. So you have to ensure your final design needs to be DRC clean. So in this case, right now if we can see, if we can troubleshoot this. So first they will ensure that this entire area is N well. So they will select that area, and this is the layer, all well P lane. So this is basically the N well. So if you want to select the layer, move the cursor over that layer and press your middle mouse button. Right. So the DRCs have been reduced from 7 to 5. So this is what I was talking about. It's an interactive DRC. And then when you keep doing this, DRC is reduced. So that we have covered this area with N well. Second, N well, over N well we have. So there is no LICON. So this is purely metal 1. So we'll select this area, and then we will use metal 1. Metal 1 is here. Right. So our DRCs are back to 0. So I select it, I will centralize it. So this is my inverter. So so this is well and good. This is all layers. So how do we know what is the logical function of this inverter? For that, we would first extract it to Spice, and post that we will do simulations on Spice in ngSpice open source tool. So to extract it on Spice, So we'll open the ticket window. We'll right now see where we are. We are in this directory, right? This is what we have cloned. OpenLane, we just standard design. So the first step is to create an ext file, extraction file. So that command is extract all. So this has said that extracting our design into sky_inv ext. So let's go to that location. Where was it? Yeah, here. And do an ls-ltr. Let's see if something new has been created or not. Yes, it has sky130inv.ext. So next what we'll do is we will use this ext file to create a spice file to be used with our ngSpice tool. So for that, what you need to do is we do x2 spice, extract to spice, and I think the command is extract to spice. Yeah, that's x2 spice. That's the command. So we use a cthresh0 rthresh 0. So doing this will extract all the parasitic capacitors also. So these are actual layers. These will have parasitic capacitors. So we'll do this. So this has not created anything new. So you can see it's the ext file is there. Nothing new has been created. Now we'll do x2 spice. That means the ext file to spice. Let's see, ext to spice finished. So let's see if anything new has been created or not. Yeah, it has. Spice file has been created. Now let's clear this window and let's see what's inside the spice file. Okay, so not much. So before we begin our simulation, let's first understand what the spice deck contains. Yeah, let us first understand what this spice deck stands for. So as you can see, we first have this PMOS, this M1000, that is the PMOS. How do I know it's a PMOS? You can see the model name P-short. Similarly, this is NMOS. For PMOS, this Y is the drain, the gate, followed by the source and the substrate. Similarly, this is drain, gate, source, substrate. So let's understand the netlist first. I'm going to draw on the screen. My drawing might be a little horrible, but I hope I can get the message conveyed. So this is our PMOS. It has got source, drain, substrate, and gate. So for the PMOS, you can see the PMOS M1000. Its drain is connected to Y. So it is connected to this node. It's important to realize here that the attributes are just nodes. It's not a value. It's not a voltage. It's connected to node Y. The gate is connected to. You see, the gate is connected to node A. The source and substrate is connected to node B PWR. Right. So this is what the first line says. We are done here. And the second line says there is an NMOS. There is NMOS. Whose right? It says that its drain is connected to Y. So that means this connection is complete. And it says that its gate is connected to A. That means these two are connected. Then it's saying that its source and substrate is connected to a node. Remember, it's a node. Its name is VGND. Node's name is VGND. So PHD. Right? Okay. Now, what all we need to do for this transient analysis? First, we would want this V ground to be connected to a ground. Let's say VSS. Then we would want a supply voltage that needs to be connected from the PWR to ground. So we will create a node. We create extra node. Say give a node a name 0, and we will create a VDD with a value of 3.3 volt. And now we have to sweep it. We give a sweeping voltage, a pulse voltage that needs to be connected between A, the input pin, and the V ground or 0. We will give it a value of the voltage value of V gain. This is a variable name. So we need to do this, and this connection. We have to define this connection. The connections which have been designed by the spice deck are these double tick ones. Yeah, that's all. Double tick ones. A and Y. We have to define the single tick ones. So we will do something. You can see if I can. I'll just remove everything. Clear the screen. Okay. Use it. Then right. So this is my screen again. I hope you can see. Yeah. First things first, we need to ensure that the scaling is proper. Right now the scaling is any dimension into 10,000 microns. So 37 into 10,000. That is not what we need. We need the values to be in the grid value which was specified in the layout. Since if you recall in this spice we had extracted from the layout. So the layout, minimum value of layout window is the measure, the grid here. So this is the measure of any measurement that needs to be taken in the spice file. So zoom in a little bit, we'll see this box, one box, and see the dimension of the box. Dimension of the box is 0.01. That's why we edit, where was it? Sorry. We edit the scale to 0.01. Any measurements will be with respect to this. So the width will be 37 to 0.01, I think it's 0.37 microns. So this is done. Similarly, now we have to include the PMOS and NMOS lib files. So for that you do dot include And if I recall correctly, it's inside the libs folder. CD libs. Yeah, these two files. So to specify that, we have to do /libs, go to libs folder, and for pshort, similarly, we'll do the same thing for nshort. nshort.lib. So these two files are included. We will comment out this, or else because we are trying to input the controls also, transient analysis also in this netlist. So we'll put it as a command. This is fine. This definition is fine for both the transistors. Now we need to make the definition for the supply voltage first. So we will create a variable VDD, which is connected between VPWR and the node 0, which has a value of 3.3 volt. So this creating supply voltage. Similarly, we create a V ground. V ground is already there. We create VSS. That is the voltage connecting between the VGND and 0. VGND and 0, whose value is 0 volt. Fine, the ground and the supply is done. Now we need to specify the input pulse. We get a value of VA, it's a VA, which is connected between the gate and VGND, which is now equivalent to the node 0 having a value of 0. And this is how we give a pulse value. The pulse low value is 0 volt. Pulse high value is 3.3 volt. Pulse starting point is 0 nanosecond. The pulse is rising, the rise time is 0.1 nanosecond. 0.1 nanosecond the fall time. This 2 nanosecond is the on pulse width, and 4 nanosecond is the time period. This is how we define pulse in the SPICE deck. And post that, we will also include the type of analysis which we want to do. So this I have already. This is the analysis. This is how we specify the analysis. We do a .tran. .tran is for the transient analysis from 1 nanosecond to 20 nanosecond, and then you run it. So this is how you create the flow for SPICE deck. So we need to run this in the ngSpice open source tool. So before that, we'll just see what is inside the model files. So as you can see, this model files actually starts here. So this is the name for the model file, pshort underscore the PMOS model name, pshort underscore model.0. So you can see all the parameters that is defined under this SPICE model file. There is one more small modification we would have to include in our SPICE deck. As you can see here, this M1000 I had told you is a PMOS. How does the ngSpice know it's a PMOS? By using this. But this is not the model name for PMOS. What you saw in the SPICE model file was this pshort underscore model.0. Only when you specify this will it we'll take all the SPICE parameters from the model file and assign it to this model into the simulation. Similarly for NMOS, it's .0. Now I think our SPICE deck is ready. To run our SPICE simulation, what you do is ngSpice, that you can open the tool and pass this as the source file. So you can see these are the values it has taken. Now to see the plot, you have to do plot. What do you want to see? You want to see the output versus time, sweeping the input. Our output is Y, time is the time period, and the A is the input. Now this is what we get. Okay, we can see some spikes around here. We will do one thing. I think the C load is very less. Let's open the SPICE file again. The C load is what you define between the output pin, that is Y pin, and the ground. So which is here C3, that's 0.24. Let's give it some higher value, say a 2 femtofarad. That seems reasonable. Now let's run the SPICE simulation again. Now let's plot output versus time, sweeping the input. Yeah, a little better. So now that we have our transient response, our next objective is to characterize the cell. So characterizing a cell means to find the value of 4 parameters. We would need to find the value of a rise transition, that is the time taken for output waveform to transit from a value of 20% of the maximum value to 80% of the maximum value, VDD. Similarly, the fall transition is the time taken for the output to fall from 80% to the 20%. Similarly, we have 2 more values, that is the fall cell delay and the rise cell delay. That is also called the propagation delay. So that is the time difference between the 50% of the difference between 50% of the output and 50% of the output. Now, when it's a cell fall delay, it's the difference between the time period when the output has fallen to its 50% and when the input has risen to its 50%, that time difference. So it might sound a little confusing, but I will show you one of each. So to begin with, we will first check what is the rise transition. The rise transition is the time taken for the output to rise from 20 to 80% of the maximum value. So the maximum value right now is 3.3. We have defined in our SPICE deck. So a 20% of 3.3 should come around 0.66. So 0.66 is somewhere around here. To select a particular region, all you have to do is just use your right mouse button. Right mouse button itself creates a box, unlike Magic, where you have to first click the left mouse button, then the right mouse button to make a box. Here, just the right mouse button creates a box. It will open up a new window. As you can see, 20% value is 0.6. So this is, let me just to zoom it even more. So this should give a better value. Yeah, that is 660. Yeah. So let's click here. So when you click on this point in the ngSpice window, you can see the values getting printed. So 0.66 y value for that. The x value, that is the time, is 2.18. Let's go back. We close this one too, not the main one. And the 80% should come as 2.64. That should come somewhere around here. 2.64. Zoom it up a little bit. 2.64 values here. Now let's check 2.64. Yeah, values 2.64. Difference between these two values, this x0 value and this x0 value, should give you the rise time. So that should come around 2. I'm just using my calci. 2.4. Sorry, 2.245. That is minus 2.18. That is 0.064. If I'm not wrong. 2.245 minus 2.18. That is 0.064 nanosecond. Similarly, you can find the fall transition. That means when the output falls from 80% of the value to its 20%. The difference of those two values will be the fall transition, and it would be as one of the assignments. Now let's check for the cell fall delay, which is the propagation delay when the output is falling between 50% of the values. I will just do rise for both. So when the output is rising, 50% of the rise, that is 50% of 3.3 is 1.65. So we will find the time difference between input and output, then the value is 1.65. So I think 1.64 and 1.66. Zoom it a little more. 1.65, yes. Now the 50% of the output is crossing at this time. Click it. For the input, it is this point. Now when we go to our Spice window, you can see, yeah, these two values. Now the difference between these two values will give you the cell rise delay. That is propagation delay when the output of the cell is rising. So let's just calculate 2.211 minus 2.150. Yeah, that is 0.061. So that is our cell rise delay. So the same way you will find for cell fall delay, it will be following in the assignment. So yes, you have successfully characterized a cell for a given temperature. Right now the temperature you can see here is 27 degrees Celsius, the room temperature, normal temperature. This is how the characterization actually works. You have actually got a taste of how the library characterization work in the VLSI industry is done. It's done for different process, for different PVD columns, process voltage and temperature, and that's how the timing library is built. So our next objective would be to create a, this is our layout, right? Just zoom in. Shift Z to zoom out incrementally. So now S. So this is the layout which we have. So we have characterized our inverter. Our next objective is to use this layout and to create a LEF file. And that LEF file we will be using in our OpenLane. And plug this cell. We will make a custom cell. We will give it a custom name, and we'll plug this cell into our Pico RU32 core, and we'll see if OpenLane takes our cell or not. What are the challenges we face? So that will be the next which will be following up. Hope this was a learning session. This is where you actually do something new. So this is a good session. This is a good workshop. I would request you to have a little hands-on on this. So till then, we'll take in happy learning.